The Meet the Author series encourages dialogue on significant contemporary questions and brings together alumni, faculty, and students to debate and discuss these issues. Today's authors, Robert Kaplan and Ellen Kaplan, began teaching with their colleague Thomas Guglielmo in a group called the Math Circle in September of 1994. They began their teaching efforts in response to the poor quality levels of math education in the country and set out to introduce and improve education for their students. Their courses have been taught in local churches as well as at Northeastern and Harvard. The Kaplans have expanded their small tutoring lessons to incorporate over 200 students and are here today to discuss their latest publication, Hidden Harmonies, The Lives and Times of the Pythagorean Theorem. Please help me in welcoming Robert and Ellen Kaplan.
Thank you.
Hello. We're not going to read a lot this morning from Hidden Harmonies, which is more a book for mulling over at leisure and letting your thoughts take off from its pictures. I did the pictures. We'll read enough to give you a sense of the great Pythagorean adventure, and then let's talk together about its pleasures and those of math in general, or the things that people find less pleasurable, which ought to be pleasurable, and also about the scary parts of this kind of thought. So I'll begin at the beginning. The Englishman looked down from the balcony of the villa outside Florence. Guido, the peasant's 6-year-old son, was scratching something on the paving stones with a burnt stick. He was inventing a proof of the Pythagorean theorem. Do you see it? Here you have 4 triangles. Here's the square on the short side, and here's the square on the longer side, and the 4 triangles and the 2 squares fill up the whole big square. Now, take these 4 triangles and shoot them off into the corners, and you have in the middle the square on the hypotenuse. So it must be, since these 2 squares are the same size, and I drew them really carefully with a ruler and all, that the square on the hypotenuse must be equal to the sum of the squares on the 2 sides. No algebra, just a picture to look at. Classically, you give those 2 pictures and you write underneath, "Behold," with an exclamation mark. "Do just look at this, do," he coaxed and cajoled. "It's so beautiful, it's so easy." And Guido showed the Englishman's son how the same square could be filled with 4 copies of a right triangle and the squares on its sides, or the same 4 triangles and the square on the hypotenuse, so that the 2 squares of the first diagram must equal in area the 1 square of the second. And the Englishman thought of the vast differences between human beings. We classify men by the color of their eyes and hair and the shape of their skulls. Wouldn't it be more sensible to divide them up into intellectual species? There would be even wider gulfs between the extreme mental types than between a Bushman and a Scandinavian. This child, I thought, when he grows up, will be to me intellectually what a man is to a dog. And there are other men and women who are perhaps almost as dogs to me. But the child never grew up. He threw himself to his death in despair at being snatched from his family by a well-meaning signora who forced him to practice his scales and took away the Euclid that the kind Englishman had given him. A true story? Emphatically not. It's Aldous Huxley's Young Archimedes, published 3 years after Sir Thomas Heath's History of Greek Mathematics came out in 1921, with its quotation from ancient Callimachus. By a happy chance, Bathycles' son found old Thales scraping the ground and drawing the figure discovered by Pythagoras. The falsity of this story isn't just in Huxley's having patched it together from what he'd read in Heath and from the legend of the brutal centurion who, sent to fetch Archimedes, killed him instead because he wouldn't stop drawing his diagrams in the dirt. It is much more deeply false. False to the way mathematics is actually invented, false to the universality of mind. It's certainly dramatic to picture superhumans in our midst, living put-downs to our little pretensions, yet testimony to more things in heaven and earth. But the actual truth has greater drama still, woven as it is of human curiosity, persistence, and ingenuity, with relapses into appeals to the extraterrestrial. This is the story we shall now tell.
The thing about math is that you never have to take anyone's word for it. It's the only human undertaking founded on irrefutable proofs. Not surprising, then, that there aren't too many of these. Not many theorems, that is, which are statements that people have come up with and have come up with proofs for. The astonishing thing about the Pythagorean theorem is that there is more than one proof for it. How many proofs would you guess there are? 357. Okay, one guess. Others? Do I hear 2,000? Do I hear 3? 2,000? Going. This is from the book. Some people collect Ketchikan beer coasters, some Sturmey Archer 3-speed hubs, others wives or ailments. Jury Whipper collected proofs of the Pythagorean theorem. He wasn't the first. 59 years before him, in 1821, Johann Joseph Ignatius Hoffmann published more than 30. In 1778, a Frenchman named Fourier included 38 among his Curiosités géométriques, and a Herr Gropp had translated others from a Russian anthologist. Nor was Jury Whipper, that was his name, nor was Jury Whipper the last. Professors Yanni and Calderhead from the universities of Worcester in Ohio and Curry in Pennsylvania gathered together some 100 proofs between 1896 and 1899. A lawyer at the District of Columbia Bar named Arthur Colburn published 108 of his own, starting in 1910. Perhaps the currents of litigation ran more slowly before air conditioning. On the shoulders of these giants still stands Elisha Scott Loomis, the boy born in a log cabin in 1852 who rose to be a 32nd degree Freemason and, quote, plowed habit formation grooves in the plastic brains of over 4,000 boys and girls and young men and women. He tells us that of all the honors conferred upon him, he prized the title of teacher more than any other, quote, either educational, social, or secret. Was he as leonine as his portrait shows him, florid mustache and wing collar? Or should we believe a penciled note in the Harvard Library's copy of his book, quote, he was somewhat high in manner, but was in reality a good sport. I never met him. Then how did you know G.W. Evans? Pythagorean investigations breed mystery. Here's another. How many proofs are there in Loomis's book? Be a Babylonian, you say, and count them. But counting, as even a Babylonian knew, is one of the hardest of human tasks. Loomis claims to have 367 proofs in his second edition, though some are circular, some defective, some no more than variations on or subsumed by others. Are the algebraic proofs, which he says readily follow from this or that geometric demonstration, to be thought of as different from them, He asks about a possible proof here, quote, can't calculate the number of others there, and speaks of several, a number of, and countless different proofs from those he gives. 9,728 proofs, for example, derive from his figures for algebraic proofs 6 and 7, he tells us, and 65,780 more from his figure 8. When he writes, as in his note to geometric proof 110, of more cases extant, does he mean more than he has given? Are two proofs really different if a square in one has no more than slid sideways from that in another? Or if a grid of lines is differently parsed? We conclude that his book contains 367 proofs minus a few, plus several, increased by a number derivable but not in fact derived, to which are added those that are other and different, resulting in many plus a multitude, increased by a limitless as well as an unlimited horde of the likely, and a slew indefinitely great that will be discovered by, quote, the ingenious resources and ideas of the mathematical investigator, close quote, giving us, as an approximate total, more than we should or could or may or want to count. This amplitude is consonant with the generous spirit of brotherhoods, Pythagorean or Masonic, and is an image of life itself. In the earth, below each tree of spreading order, the mice of somewhat gnaw, while chaos in its foliage is made by the insects of etc.
Loomis credits his 14th geometric proof to Miss E. A. Coolidge, a blind girl. He then gives us no more than a reference to the journal he found it in. What? Were his curiosity, his imagination, his compassion not stirred? Did his compulsion to move on to the next and the next and the next leave him no time to wonder at the visions of the blind? Not being in such a hurry, we hunted out the Journal of Education, volume 28, 1888, through the stacks of Harvard's Gutman Library, where it had, who knows how many years before, been misshelved. Pause for all librarians that faint. Giving the diligent librarian a dusty 2 hours before she cornered it down a stack receding to infinity. That made my day, she said. And there, on page 17, was Miss Coolidge's proof. Across from the notes and queries, what's the difference between Belfast in Chicago, Belfast in Maine, and Belfast in Ireland? What is the Aginian sect? Her proof, however, was not as it appears in Loomis, who had clearly exercised his editorial powers over he was somewhat high in manner. We give her original proof in the book with all the extraneous steps. What's particularly fascinating about this proof is that Miss Coolidge begins it geometrically, making and comparing shapes, but then turns to calculating with letters, when perhaps she can't quite figure out what's left and what's wanting. You might think that, being blind, Miss Coolidge would have resorted to abstraction as early as possible, but in fact she delays it as long as she can, trying to stay true to the spirit of geometry. Having followed her proof, if we now follow her, we may better understand the play between abstraction and different sorts of sensory information. But how find the woman behind Loomis's brief Miss E. A. Coolidge? It struck us that Coolidge is a good Boston name, and the journal in which her proof first appeared was published in Boston. Might she not have been a student at the renowned Perkins School for the Blind? We emailed Jan Seymour Ford, their research librarian, who answered, that was inspired guesswork. Emma A. Coolidge was a Perkins student. Rather small, but there is a drawing from a photograph of her. She was born August 4th, 1857, in Sturbridge, Mass. She lost her sight from whooping cough when she was a year old. She could only detect light and shadow, and some of the remedies her parents tried, having her wear gold earrings, putting talcum powder into her eyes, blistering her temple with poisonous flies, helped. After graduating from Perkins, she studied at Wellesley for a year, then returned as a teacher to Perkins, where one of her students is said to have been Annie Sullivan, who was Helen Keller's teacher. Emma married, had a daughter, wrote children's books, taught music in her New Hampshire village school, sewed, knitted, could kill and dress a fowl for dinner if her husband was away, and boldly went out alone, tying white rags to doorways so she could find her way from place to place. Isn't this what we see in her proof? Catching the chiaroscuro of prominent shapes, but navigating otherwise by those abstract relations with which practice and memory furnish the mind. What sort of imagination this is may matter here. The blind mathematician Louis Antoine was led by his advisor, Henri Lebesgue, to study 2- and 3-dimensional topology because, quoting Lebesgue, in such a study, the eyes of the spirit and the habit of concentration will replace the lost vision. His equally outstanding compatriot, Bernard Morin, who has been completely blind since age 6, was asked how he knew the correct sign in a long and difficult computation. By feeling the weight of the thing, he said. More tellingly, Morin distinguishes between what he calls time-like and space-like mathematical imagination, and surprisingly says he excels at the latter. A problem with picturing geometrical objects is that we tend to see only their outsides, which hide what might be complicated within. Morin, who works with extremely intricate objects in 3 dimensions, has taught himself how to pass from outside to inside, from one room to another. Our spatial imagination, he says, is framed by manipulating objects. You act on objects with your hands, not with your eyes. So being outside or inside is something that is really connected with your actions on objects. Think of Emma sewing and knitting, or killing and dressing a fowl. Might Emma's extraneous calculations have come from an intrusion of the time-like into her sounder, space-like imagination? And is the tactile yet one more intermediate between being and becoming?
Spatial imagination, what does this mean? What does it mean when physicists talk about string theory, about strings in 11 or is it 10 or 9 dimensions? What does it mean when mathematicians toss around 12 and 200 dimensional objects in their coffee-fueled conversations? They aren't superhuman. Like us, they see in 3 dimensions only. So let's go back 4 centuries together to look for an answer. This is now from the book. In 17th century Ulm, the master reckoner Johannes Faulhaber discovered a spatial generalization of the Pythagorean theorem and saw how it would lead him to a deeper understanding of 666, which he already knew was divine rather than diabolic. While the margins of our minds are too narrow to contain Faulhaber's Kabbalistic proof, we will unveil to you his rectilinear pyramid. Analogy said his contemporary Johannes Kepler, is my greatest of masters, moving by analogy from squares on the lengths of a right triangle's sides to squares on the areas of a right pyramid's faces. He came up with this beautiful generalization of the Pythagorean theorem. Given such a pyramid, now this is a pyramid where the sides, 3 of the edges meet at right angles, the sum of the squared areas of these faces, A, B, and C, would equal the square of the area on the hypotenuse face, D. A squared plus B squared plus C squared equals D squared. If not quite up there with 666, still pretty wonderful. In the winter of 1619, Descartes, passing through Ulm, may well have met Faulhaber. Local legend has it that one night, dazzled by Descartes' brilliance, Faulhaber reached out. I picture them as sitting on opposite sides of his fire in the cold winter night, and touched his guest to make sure that he was human and not an angel. Wouldn't you have done as much were your visitor to have mentioned that this theorem also held in 4 dimensions? Well, geometry is the one open road in mathematics where we know things intuitively from our experience, we know what's likely to be true, and we can stride confidently into trying to prove what we're convinced is real and true. But what does it mean to talk about objects in 4 dimensions, or 5, or 6, or the Pythagorean theorem being true in 271 dimensions, or 10,000 dimensions, or infinite dimensional space? All of these statements have been proven. But what does it mean? What does it mean to you? What does it mean for mathematics? What does it mean about the human mind? What does it mean about mathematics, which is the art of the infinite, where this most beautiful, this most telling of the arts is long treated as Cinderella sitting by the fire, thought of as being frightening to some, boring to others, or a combination of both to many. Let's talk about whatever you'd like to talk about, Pythagorean theorem, or how mathematics is taught or should be taught, or what it's all about. What are your questions? Do you want to go over the number of proofs of the Pythagorean theorem?
Or should we just say, math, wonderful. Math, scary. Math, I don't want to say anything about it for fear I say something wrong.
Well, what we found with we began the math circle at Harvard in 1994. We now have students ranging in age from 4 to in their 70s.
I think it's worthwhile saying we began it because Bob was teaching smart university students. I was teaching smart high school students. They could all, Greek was child's play to them. But if you said something like derivative, it was completely terrifying. And they also felt very strongly that if you were a math student, you were of necessity passive. That you sat there and copied down what was written on the blackboard, which, by the way, has now disappeared, since usually people are just handing out the photocopies of their notes. So you wonder, why am I sitting in this room hearing him say those things that I have in my hand? But that's yet another issue. But the idea of math as deeply inaccessible, that it has to be presented to you, and then you either get it, which means you do well on the test, or you don't get it and you do badly on the test, and it's probably genetic anyway, so it's not your fault.
And you feel horrible for the rest of your life.
No, really.
Yesterday, we had our first math circle class of the semester classes, and with the 4-year-olds, we began by saying, are there numbers between numbers? And they said, well, no, of course not. There's 0. Well, they didn't know about 0. There's 1, 2, 3, 4. We said, right. And drew a long line on the blackboard and put a 0 here and a 1 over there. I said, anything in there? No, of course not. Erase the 0 and 1 and put a 4. This is a class of 4 to 5-year-olds. Put a 4 there and a 5 there. Anything in between? No, no. So I started drawing a palm tree. And a girl said, "You can't do that." I said, "Well, I'm doing it." She said, "No, no. It's not that sort of thing." Now that's a wonderful insight. The number line is not like a horizon in a desert. So I said, "Okay, no palm tree. Is there anything in there?" "No." "How old are you?" I said to one of them. "I'm 4. I said, "Oh, happy birthday. Today's your birthday." "No, I'm 4, but it's not my birthday." "When was your birthday?" Back then." "So are you exactly 4 today?" "No, I'm 4.5. I said, "You're 4 and a what?" "You know, midway." "Ah, midway between." So I made a mark closer to the 4 than the 5. And I said, "You mean like this?" "No, no, move it over." At this point, they're taking over. They're going to teach us, we're their nice but slightly dumb friends at the board. They can teach us things. Putting them in power, letting them invent mathematics in the only way it can be invented, as it turns out.
There's one wonderful little girl who says, "Now, Bob, you know that's silly." And she's quite frequently right.
Yes. Was there anything between 4 and 4.5? Well, there had to be now, but who knew what it was? Well, it was the middle of that. Yeah, but what do you call it? Well, they don't know about fractions. So they invented their own signs, weird signs.
But then we went into the wonderful gift of nature, which is small children eat their sandwiches in quarters. And so we had a sandwich, and we cut it in half, and then we cut it across the other way and said, what would those be? And those turned out to be quarters. This has failed only in England, where they cut their sandwiches diagonally. And you can have quarters, but they don't look like quarters.
So we discovered yesterday that there's something between 4 and 5, and probably between, therefore, 0 and 1, too, but we haven't checked it. There's a half, there's something, but we don't know quite what it is between 4 and 4.5. We'll go on to get 1 over various powers of 2 in this way. They're so excited they didn't want to leave at the end of class. And class is at the end of the day for these 4-year-olds.
And it's an hour long, from 4 to 5. If anybody has had any experience of 4-year-olds, that's not their best time.
We'll go on next week, or maybe the week after, to thirds. That'll be a wholly new thing. And again, no, there can't be such things. And then the great crisis will come halfway through the semester when we'll ask which is bigger, a half or a third. And if they run true to form of the past, they'll say, well, clearly a half is smaller because 2 is less than 3. And we'll nod enthusiastically, and they'll know that if we nod, it probably is not the case, and they'll have to work it out for themselves. What happened once was there was a bitter battle between those who said a half was bigger and those who said a half was smaller than a third. And those who said it was bigger said it because we had nodded and we were authority, and those who said it was smaller said they just felt it was intuition, like Emma Coolidge's, but they didn't know why. We went home, all of us in despair, came back the next week, and a girl raised her hand and said, make a circle on the board. And we thought, oh, her parents have told her what to do. We had been talking about it being a pie, and so we made a circle for a pie. She said, now, make the Mercedes symbol in it. And over there,
it's Cambridge.
Yeah, right. Make another pie and make a line down through the middle of it. You can just see which is bigger, unless. And so we said, well, which would you want a part of if you were one of the people sharing this? So, well, she would want the one from the 1/2, unless, she said, it was a kind of pie she didn't like, in which case 1/3 is bigger than a half. Not something we'd ever encountered before.
But deeply true.
So, yes?
Would you like to comment on the teaching of calculus that everybody aspires to? I fought for years to try to not have that be a requirement, but in fact, algebra be the
Yes.
thing that people emphasize. Would you like to talk about the
Love to.
curriculum relative to calculus?
I would love to. Having taught calculus and found that you know, it's made to be the be-all and end-all of mathematics, as if there were nothing beyond it, when
Well,
in fact...
no, I think it was the be-all and end-all of mathematics in the 17th century. I mean, nothing wrong with the 17th century. I far prefer Mozart to some of the people who were practicing down the hall. But there's a historicism to curriculum building. And there's also an amazing, I don't even know the word for it, I was going to say inertia, that we always teach calculus to the 12th grade. We've always taught calculus to, ancient Greeks must have taught calculus to the 12th grade. That's the way it is. And also, it's hard. And so, when I was at school, the great sheep versus goat divider was whether you took Greek or just Latin. Now it's calculus. Calculus is what you have to have on your transcript to be taken seriously from a school.
And yet, there is, as you're suggesting, and I completely agree, we have these two gigantic trunks of mathematics, algebra and geometry. Of course, they do grow from a common source. And
their branches do intertwine.
Their branches intertwine, and many branches come off them. It's also true that anything leads to everything. You could immerse yourself in calculus and come up with wonderful insights. You could look to find the sum of the first n integers and do it by taking the second derivative of what you're seeing. But that's awkward, unintuitive, hard. Why not stress the structural aspect of mathematics? Why not see that algebra and geometry are two different, and yet, thanks to Descartes, translatable one into the other, sources of our intuition? And see geometry as leading to calculus, see algebra as leading to calculus, and to many other cross products. So yes, I think we're all being the dog wagged by the tail of MCAS and state and national requirements, which have, where on earth, I suppose the history of how calculus came to be the center would be interesting or frightening to read. I don't know what it is, but we're trapped in that. And it would be great to get out of it.
It's also an odd thing to do in this country. I mean, if you look at China or if you look at Russia, which are enormous countries with smaller resources, to say what we need is something that'll wipe out all of the non-succeeders so we don't waste time sending them to college. That could almost be morally justified, but you'd have to dance pretty fast. This is not the problem in America. You do not have thousands of people battering down the doors of universities to study mathematics. And so to make it as unpleasant as possible so that people will stop doing it seems particularly foolish.
When here it is, something which is in our instinct, it's in our bones. It's what we call in our book, on our math circle, Out of the Labyrinth, we call the architectural instinct, which we all have. To develop that instinct through graph theory, through sequences, through series, through the Pythagorean Theorem, any one of these many routes, putting down fish lines with hooks on them, and if this one interests someone more than that one, fine, pull up that line.
I'd go for geometry simply because I do feel, as your line, it is the great open road to mathematics. It doesn't really frighten you to look at that picture. And it doesn't really frighten you to say, what's going on with those triangles? Huh. I mean, this is tangrams. This is 15 puzzles. This is something that people actually do for pleasure. And also geometry is the field in which proof is really easy. And if there's anything that generalizes from mathematics to what we laughingly call the real world, it's that you shouldn't just make a statement. You should be able to prove a statement that you make.
Now, one thing about this demonstration, you could question it as a proof. We haven't traced down the steps in it two big squares are the same, so moving things around within them will leave the same areas. We haven't traced that down to axioms about
We could have
area.
cheated by having thick lines so that there really was more space in these two, but the line just covers it up.
Relying on the visual might not be the best thing to do in the end. There's a beautiful proof that 64 equals 65 by drawing a rectangle with a diagonal if you just draw the diagonal thick enough. So one does want to get to proof. It's the one thing that distinguishes mathematics from politics and religion. Does this square with your feelings?
I didn't succeed because I realized the other faculty involved just said, oh, it's good for them. It's a good lesson. And I took much math and beyond calculus even, and I thought it was useless. But they made it very difficult, and I thought turned off many students.
I think it turns off many students. I'm not sure it's useless. Euler, the great Euler, said everything in the physical world is either maximizing or minimizing some process, and calculus lets one come to grips with what that means, what maxima and minima are, how to find them. It's beautiful, but it is only a small part of mathematics. It's as if we were to devote all of mathematics to tangrams, to Sudoku, which are wonderful, but a small part of math. Other points, questions? Yes.
I teach calculus here in the freshman cohort. These are actually my students. And when I would just add in, obviously I love math, but it wasn't always the case. I remember being a freshman in my calculus course and dealing sort of, I think what you might be implying. I mean, I would have professors who would essentially speak. I'm from the city. I'm from a very urban city. And from Lowell, and when I graduated from high school and got accepted into UMass Lowell, I think people don't talk about it, but except the students, but we generally felt that calculus was the leading out course, and that there was a feeling, and I see it here with the students. I see it every school that I've been at, whether it's a student teacher. There is something that just occurs in the classroom that it seems to be like a talking down to the student.
Yes.
Almost like that my professor was as a freshman, that calculus is this, or math in general, is this thing on a mountaintop.
Yes.
That you will never be able to comprehend, and whether that's from the administrations that bring that viewpoint into the school, and then you have to reciprocate that in the classroom. I don't know where it comes from.
I think some of it comes from, and when every once in a while catches it in one's own heart. I did it, and they're going to do it. It made a man of me. Oh, whoops, it didn't. But I mean, that kind of line of it's important for people to have unpleasant things. And then there's also the number of people who, unable to teach other subjects because of a lack of human.
Exactly. And this is the disease that runs through mathematics.
Yes.
Professors, that we tend to be, the one half of the brain using people. We become some of the most, I'll put myself on the line, some of the most boring people that you'd ever want to have teach a class, and you have this right brain, left brain kind of thing, and there is this access to the other side of the brain that doesn't seem in place with scientists and mathematicians, where we are some of the worst teachers that you possibly want to teach any class.
Our son
But that is also why they trash geometry, because it's just a picture. It doesn't have any meaning. Whereas
our son had a math teacher, and one day our son said, "I'm sorry, I just don't get this." And the teacher said, "You don't get this? I get it." That was his explanation. Thanks. Math is the great put down. When here it is, it's so beautiful. It's an art, and it's something which everyone should, could, can have access to, if allowed to play rather than to compete, if allowed to explore at leisure, if allowed to make mistakes. I mean, a mathematician is wrong 9 times out of 10. It's that one time that works that matters. That's great. What a feeling. Then there's the next day when you're back at scratch. So
also, mathematicians have no shame about getting things wrong. And the way school math and college math is often the grade is what tells you whether you're a good person or a bad person. And therefore, you're not going to say, I didn't understand that, because,
And I tell my own students, I said, what is the, I don't remember exactly what the Einstein quote where he says, you think they're having problems with math. see what I'm dealing with. We just have made more errors than they have. That's what makes us teachers. We hopefully save them some of the errors, but we want to encourage them some of it as well.
Yeah. To pick up another point of yours, the second chapter in our book on the math circle, Out of the Labyrinth, is called Cod Liver Oil. That it tastes bad, so it must be good for you. That old way of thinking, yes?
Hi, kind of on the flip side of that, have you encountered a lot of people who kind of just throw up their hands and say, I'm just not good at math, or I can't do it? And how do you avoid that mentality from being spread, and how do you combat it once someone kind of manifests that?
That's
It's
such a great
absolutely
question.
at its worst in England, where when you are 10, they decide, are you science side or are you arts side? And then you're permanently, right on your forehead, it says. And surprise, surprise, practically all the girls end up arts side, if you remember back when you were 10 or 11. And
And it's the analogy he just made with the children. Is there anything between here and one? You know what I mean?
Right, right.
You're either
Yeah.
this or you're that. There's
Yeah.
nothing.
Yep.
That's
yep,
right.
Yep. But it also does give you the feeling that you are either genetically or part of your brain is different or something like that, and that there's no possibility of even conversation between the arts and the sciences.
The number of parents of math circle students who say, well, I'm so glad my son or daughter is good at it. I'm no good at it. My parents weren't any good at it. It's genetic. It's not genetic. Is walking, putting one leg in front of the other, a genetically passed on skill? We can all do that. Math is like walking. We couldn't tie our shoelaces. We couldn't walk straight ahead unless math were built in. So how does one combat that? By, again, turning it over to the kids, putting them in charge.
Can I talk about my class last night?
Oh, yes.
My class last night is 10 10-year-old boys. There used to be a girl, but she raised her eyebrows at me and left for another section. And they are bouncing physically all the time. They are talking all the time. They are saying, I think I've got an idea. Can I come to the blackboard? Well, they come to the blackboard, and the architect of the Harvard math building decided that mathematicians were giants, and the blackboard starts about here. So I can write on it, but they have to stand on a chair to write on it, and you see them busily working away. The question was, what's the sum of 1 plus 2 plus 3 plus 4 up to 10? And could you do it without brutal arithmetic? And they came up with about 6 different methods. And this was the amazing part, given 10-year-old boys, then they went and sat down and each one explained his method, and the others talked about it and commented on it and said, that's a good method, have you thought of doing this? And that's a kind of conversation that turns math into not just a human activity, but a humanist activity. You're involving people, and you mean he thinks differently from the way I do?
You mean he exists? To give you an anecdote which I think is very, very encouraging, you're probably saying to yourselves, well, yes, sure. Those kids are self-selected. It's greater Boston area. It's Cambridge. Those are kids who want to be there. We were asked if we would try out our math circle approach at the Suffolk House of Correction. And we said, oh, sure, I'd love to do that someday. Yeah, we'll have to do that next month. Well, we're busy for a couple of years.
Terribly busy, and the weather's bad.
The person was very insistent, and one day we finally went. And it's very frightening, if you've ever been inside a prison, just to get in when you are searched and fluorescent lighted and stamped and so on. Going past the guards who are sitting in their standing in their A form with hands on the guns on their hips and looking you over, I can take him out. Guards much more frightening than prisoners.
They dress the prisoners in different colors depending on their
degree of violence.
Yeah, I guess that's it. So if you walk into a room and there are 3 reds, 2 oranges, and a yellow, you're in trouble.
So we were led into a small room, a quarter the size of this, and left by our mentor. He walked away.
The people are gigantic because, oddly, one of the things they do teach in prison is bodybuilding.
So 20 very, very large, and to us frightening people came in and sat down and glared at us. And we had tried to figure out how to begin and what to say. What we wanted to do was the sum of the first n integers. So I said, "Oh, math, boy, is it awful." "Yeah, right on." They ask you what 1 plus 2 is. Somebody says, 3. I say, yeah, 3. And then they ask you what 1 plus 2 plus 3 is. It's 6. What do you take us for? So I say, oh, of course, we all know it's 6. And then they ask you, and now Ellen is writing this on the board, what's 1 plus 2 plus 3 plus 4, all the way up to 20. At which point there's this slam of a hand on a table. I'll leave out the expletives. That's what it is about this math. They ask you these damn fool questions nobody could ever answer, and what's the point of it? All you're going to get is a number. And we said, right on, absolutely. It's so stupid. And it's so hard. And you're doubtless, I'm certainly going to make a mistake if I start adding up 1 plus 2 is 3, and 3 more is 6. And I'll make a mistake before I get to the 20. Pause. A couple of right-ons. And then Ellen said, there's got to be a nice way to do it without all this work. There must be a simpler way. Conversation, mutters, grumbles, nudges, looks. Conversation, somebody said, well, you make 10 bonds. What are 10 bonds? Well, 1 and 9 is 10, and 13, 7 and 3 is another 10. So we made 10 bonds, drew lines down, did all the 10 bonds we could, and ran out of them. Now what? Well, you can make 20 bonds, 1 and 19. No, we've already used the one. Oh, that's not going to work. So more conversation. And then someone who hadn't said anything, he was smaller than the rest, said, look, I know this is wrong, but, and whenever someone says that, they've got it.
Because it's an idea they've had. It's not something searching the memory and trying to come up with what was I told.
He said, look, 1 and 20 is 21, and so is 2 and 19. And I said, sheer chance. And another person said, ain't chance, because 3 and 18 is also 21. Someone else says, they're all 21s. Ellen says, what do you mean all? All those things. What things? The bonds, the pairs. Oh, all the pairs are 21s. How many pairs are there? Well, there are 20 pairs. No, you idiot, there are 10 pairs. So there are 210, says a voice in the midst. High fives all around the room. Can we do more? Sure, you want to do 1 to 100? Yeah, well, it's 101 times 50. It's 5,050. Can we do more? At the end of this, for us, frightening, for them, exhilarating hour, they didn't, this was better than bodybuilding. They had done it. They had invented it. They saw it was true. We obviously didn't do a proof, but the proof was right there. And to feel empowered in that way, to feel that it's not imposed on you from without, but given from within, that you can invent math, and you invent it in the only way it is, that mind and world have met across this osmotic membrane of mathematics. What a feeling. I hope that's an encouraging anecdote.
If you look at a math book on any level from pre-kindergarten, it almost always says, here is a rule, now apply it to 25 examples, which you'd never do in your real life. But if you simply turn the page upside down and said, here are 25 things, what are they examples of? You would be getting people to think in the way in which we have to think in every other part of our lives, where you say, what's an underlying principle? What's going on here? I think the line, what's going on here, would be better than having the times tables on the blackboard.
Yeah.
Yeah.
I think the thing that I was thinking back to the calculus versus algebra sort of discussion, my experience, I was very good at math in high school, grade-wise, could repeat what I was told to do and process a little, move things around and get the answer, But I think algebra always made a lot more sense to me than calculus, because with algebra you could have word problems, and it would say, Jimmy has these 3 grades on a test, and there's one more test, and he needs his average to be 85, so what does he need to get on the 4th test? And you could understand this is a real-world situation and apply something to it. Well, how are we going to figure out what he needs to get on the 4th test? And when I was taught calculus, I know there are real-world applications, but we were not given those same kinds of,
Yes.
well, okay, here's a situation, and how can you apply something to get there in a real world? There weren't word problems
Yeah.
when I did calculus, and I
Yeah.
don't
And there,
word problems for calculus.
yes.
There are word problems, but mostly they turn out to be about physics that you haven't had yet.
But what we do with our 10-year-olds when we do calculus with them is we say, anybody here ski? Yeah, I ski. Well, do you know that when you're going up the hill, your skis are like this, and when you're going down them, they're like this? And what are they doing at the top? Well, they're like this. Oh, right, they're level. So I guess they're level at many places on the hill? No, they're only level once up at the top or down at the bottom. Oh, that's interesting. So we're talking about tangent lines and their slopes in a very real-world way, which is utterly intuitive to bicyclists as well as skiers. And that's going to lead to saying, well, I wonder if we could figure out, what the various, inclinations, angles are, and whether that matters, or whether we just need to know the top and bottom slopes. And then it becomes imagined. If the whole thing is to make this imagined rather than mechanical.
Which is hard in schools because a lot of the people who are teaching math in schools are not very comfortable with math themselves. And they will have the answer book open on the desk in front of them. And so they're waiting for the right answer.
We've certainly found with public school teachers, in many encounters, most of them are scared to death of math. And what they're very good at teaching...
You mean elementary school teachers?
Elementary school teachers. What they're very good at teaching is their fear of math. That they really get across. Yes?
I was a little scared of your comments on proofs. So I do proofs, but you said that in math you can always prove things, you can always check it out. But I can't check it out. I can't check out the proof for Math's last theorem. I take it on faith. I know little pieces of it. And then you said that's what we should do in the rest of our life. There's quite a controversy in it, and that you can read articles, Thurston's article on what is proof and stuff like that. So there's kind of a controversy about how you do proofs, how you communicate them, and there's one person who wrote out a proof, the famous mathematician, and he said, if anyone can tell me what this is really about, please let me know. So, what is this about proof? And do you really think that I should apply it in the rest of my life?
It's such a good question. The tree of proof just goes endlessly down as its branches go endlessly up. And how far down do you have to go to make sure the tree is firmly rooted? There was someone who taught at Northeastern 20 years ago, a constructivist named Gabe Stolzenberg, who said, these proofs in calculus aren't worth the paper they're written on because they are proofs by contradiction, establishing that something exists, because if it didn't exist, you get a contradiction. And what kind of a proof is
the absolute
that?
classic was this. He says, if you have a curve, and you have a point below it, and you have a point above it, we would all agree that if I drew the line between those 2 points, it would pass through the curve. Nod, 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 yes?
The intermediate value theorem.
And he says, unless you can say where the line passes through the curve, you can't say that it has passed through the curve.
The only proofs of the intermediate value theorem are proofs by contradiction. I think Brouwer showed that there cannot be a direct proof. So what situation does that leave us in? To make that more vivid, if you are in a foreign town and you've heard there's a very good restaurant, and you stop someone in the street and say, could you tell me the way to such and such a restaurant? And he says, yes, I can. And he walks away. Well, he's answered your question, can you tell me? Yes, I can. But you don't know where the restaurant is. You'd like a proof to show you, to be able to allow you to construct that which it's talking about.
And you'd say at the end of it, not only, oh, that's why it's true, but now I see why it's true, and now I could do something with it.
I think like this proof up here, what you were saying, it appeals to your other senses. It appeals to the other side of your brain, as you were saying earlier. When you answer a proof, that requires a higher level of math, kind of like you just said, you have to go further down. That's only helping the mathematically inclined to understand that problem in the first place, and that's why it's unapproachable for most people.
Yeah.
That has real value.
It really does.
It's intuitive.
To prove that the sum of the first n integers is n times n plus 1 over 2, there are lots of proofs, but some are inductive. Induction is a weird process, not intuitive, whereas the tie the first to the last and see how many pairs you've got, as long as they're an even number of terms. Once you have an odd number of terms, you've got to do a little dancing.
But I even do that with drawing. I mean, I draw the squares and dots,
Yes.
it becomes a visual thing.
Yes, triangular numbers. It's wonderful, and people love that, don't they?
Sure.
Yeah.
One of the Pythagorean proofs there's one on YouTube with, I'm sure you may have encountered it, with water.
Yes.
You can prove without words, so you see the
It's in the book.
those are the ones that sort of strike you. My own interest is the connection of music and math. And so for me, music and math are sort of the proof for each other.
Yes.
But I always feel handcuffed because I don't necessarily have the privilege of teaching a musically inclined class. So you can't just break out every example and start doing music with it, and vice versa. You can't take a lot of music students
Yeah.
necessarily. Let me show you the math of it.
The wonderful thing about the Pythagorean, why our book is called Hidden Harmonies, is because it is utterly musical in its nature, the Pythagorean quest. And of course, there's so much of Pythagoras in musical theory and in musical composition. To answer your question a little more fully before I leave it, we're only in the 21st century. I mean, we have, 3,000 or so years of math behind us, or 4,000, and all that ahead. We're awfully young at this art. We don't really see how to unite the intuitive and visual with the abstract and algebraic. We're moving slowly toward it, but 2 steps forward and 1 step back. There was a hand. Yes.
I was just going to comment further on, that's my comment. So, yeah, like.
Aspects. It's dangerous because they can be wrong. When Cantor came up with his set theory, the different sizes of infinity, when he first showed that there are more reals than there are counting numbers, published proof, his colleagues in Germany said, "You're out of your mind. This is stupid. It's wrong." And he said, "Well, could you show me where?" Well, I can't point to where, but it's wrong.
They actually suggested he check into an insane asylum. This proved he was no longer capable of.
And even today, there are people who say, "Well, it just doesn't feel right. You can't talk about completed infinities the way he does. Why can't you?" You can't. Sounds like politics or religion again. So yes, we're very much in the midst, having to take things on faith, qualified faith, faith in people we trust, in hopes of making it someday so that anyone, maybe thanks to the internet and Wikipedia, could trace down any statement all the way down to its undeniably acceptable foundations. A plus B is B plus A. Well, I'll take that on faith. But it's a funny kind of faith, those axioms. You had your hand up.
I was going to comment about that proof.
Yes.
I look at it, and to me, it isn't intuitive. Now, I would comment, though, I think you could make it clearer if you were to color it in.
We've
Triangles with red and the squares yellow.
Yes.
Then it would be easier to translate.
Very good point.
And it would be super if you had a little wooden tray and real wooden triangles. And if you walk past the Cambridge Trust Company in Harvard Square, you can see one that Bob made.
Oh.
You can't get into the window and move it, but
Unless
once
you want to rob the
have
bank.
movable objects, it'll convince
To
you.
move the triangles around.
You can add sound in, you can play that, you can play that, you can hear that. But that is absolutely 100% true. You can play that.
Absolutely.
Music of that proof correlates to the color that you can see.
That's really nice.
Time is up.
Well, I mean, everything is ultimately waves, and the waves that you hear and the waves that you see have a correlation. And once they're established, you can play the proof the same way that you can draw it. It would essentially be mapping a color, the wavelength of the color from the sound.
Oh, that's awfully nice. I'd love to go on forever, but I'm afraid I'm afraid
Our time is up.
time is going fast. Thank you very much. Thank you.